Okay, good. There we go. Okay, so I am recording everything. So if you can't make it for some reason, or something happens, I will post the recording of what we did on that day. It will also be a YouTube video as well. Okay, so that should kind of help out. Okay, so chapter 4. This was the big chapter. This was where we did all the reactions. I still am going to encourage you guys that you should still make that note card that I talked about in class. And I know a lot of you have probably already made it in the meantime. It really, really helps in the organization of these reactions. Because as we start adding more and more chapters, when you do a synthesis problem, even though you guys have open notes, I really want to stress, just because you have open notes doesn't mean it's easier. Okay, I saw a question there saying, am I going to make the exam harder? I don't have to. It's going to be pretty challenging as it stands. Because just because you're allowed to have open book, it doesn't mean you know where to actually find all the information, especially on a synthesis problem. Because I can ask those in an infinite number of ways. It might not be a problem that's in the book or that you can find online or anything. You have to know how to line up all of those reactions. So please, just because you think that this is online, you still have to study and do the homework and prepare yourself. Okay. I want to put that out there. The first reaction we talked about was the addition of HX and on a double bond, and we talked about the mechanism where the double bond attacks the hydrogen. So your Lewis base attacks your Lewis acid, and it kicks out the chlorine. And it gives you a minus charge on the chlorine right there. And it gives you a carbocation. We talked a lot about carbocation stability. And then the chloride attacks there in order to form your alkyl halide. All right. We talked about Markovnikov's rule, where if you don't have equal substitution, I don't think I'm going to do the pen, because if I do the pen, I can't move anything. So actually, let me see if I do pen in. That's just the highlighter. Text. No. Okay. All right, that's fine. We'll just do as is. With Markovnikov's rule, the more substituted double bond is where the halogen goes. All right, so you either can have the halogen at the least substituted or the bromine at the more substituted. It goes to the more substituted. That is Markovnikov's rule or Mark's rule. This is just kind of showing how both the HBr is able to add, and it's going to be where, because remember the mechanism, you form a carbocation, and you're going to form it on the more stable carbon, on the more substituted carbon. So the hydrogen adds first, so the hydrogen is going to go to the least substituted, making a carbocation on the more substituted, so that's where the bromine is going to go. Okay? And so here is the reason why. These are the substitution. Remember in class we also went over the substitutions of a allylic and a benzylic carbocation as well. So make sure that you have that list and you remember that list. So you still have primary and secondary and tertiary, but then the allylics are more stable than the aliphatics. Remember, these are the aliphatics. Then you have the allylics, and then you have a benzylic, and we said the reason was because of resonance. Those molecules have resonance, and we talked about that. Resonance is quite stabilizing, so that's the reason for that. All right. Again, if you guys have any questions, please put on your microphone and ask me so that we can go over it. Okay, so that is all the slides for that particular section. This is 4.3. All right, next reaction is the addition of water. Same type of thing. Your double bond grabs a proton to give you a plus charge. Water then attacks the plus charge. Remember, in this case, you have this hydrogen, this extra hydrogen here that water has to come over and pluck off to reform a hydronium ion. All right, and remember, the acid is used. You can't see. Okay, thanks for letting me know. You should be able to see that sign. You know, I'm just going to activate the screen, so you should be able to see everything on my screen. There you go. So I don't have to worry about that anymore. Okay. Sorry about that, guys. Thank you. All right. So it's the hydration reaction. So remember, we had to use an acid catalyst. Pull the chat up. Okay. So it uses an acid catalyst. So the first step is the pi bond grabs a proton to give you a carbocation. All right, and then the water is going to attack that carbocation. Okay, and remember, you have a plus charge on the oxygen because you have this extra hydrogen. Water comes over and plucks that off to form acid. Remember, that's regenerating the acid catalyst. All right, if you remember, these are all the ways that they show acid catalyst. Either they say the word acid, or H3PO4, H2SO4, or H plus, or H3O plus. So those are all the different ways of showing the exact same thing. All right, and then you eventually get the alcohol. This also goes by Markovnikov's rule. So the double bond, grab the proton, you get a plus charge on the tertiary, opposed to getting a plus charge on the primary, which is less stable. And then water attacks, pluck off the hydrogen, and you get the OH on the more substituted position. All right. However, there is a way that you can do a least substituted reaction. With anti-Markovnikov, it's BH3. Looks like that's hard to see, so let me just remind you what that is. That is, not that this is going to be any better. Yes, this is really hard to use. I am about to get one of those pads. I don't know if you guys have seen these pads. It's a plastic pad that you hook up to your computer and you have a pen. And you write on it, and it's actually you writing, and it shows up on the screen. So I am going to get one of those, and that might be easier to use. So that'll be. I should get it tomorrow, I think. Okay. Oh, I just deleted it. I think you guys know at this point. That's BH3. All right. And H2O2 and sodium hydroxide. Again, guys, if you can't see anything, you can hear anything, just speak up. It'd be better if you unmute yourself and talk to me. I'd rather be talked to than, because I forget about the chat, so I sometimes don't see it. Okay, so Markovnikov, acid and water, and anti-Markovnikov, BH3, H2O2, and sodium hydroxide. Remember, the 1 and the 2 means first you do this reaction, and then second you do that reaction. Where in this case, it's all at once, all together. All right, so that is it. These are quick videos. Goodness, I didn't realize they were so fast. Okay, so 4.4. There's only 2 slides here. This is the addition of X2 to alkenes. So remember, X is either chlorine, bromine, or iodine. So either Cl2, Br2, I2, R2D2. It's a good thing you're on mute because I can't hear anybody laugh. But it's not like you laughed at my jokes anyway, so it's about the same. All right, anyways, if you add Br2, remember you get the trans addition, or the anti-addition. Sorry, the anti-addition. See it down there. Let me blow this up a little bit. There. You get the anti-addition. So your two compounds are, or your compound is a trans compound, where one halogen is coming out and the other halogen is going back. And the reason is because in the mechanism, that line is hard to see, so let me redraw that. There should be a double bond right there. That double bond grabs a bromine and kicks out the other bromine, giving you the halonium ion. All right, in this case it's called a bromonium because we have bromine, and it's a plus charge right there. Plus. All right. And then the other bromine, because this bromine is so incredibly large, remember in class I talked about how big this bromine is? This bromine has to attack from the underside, the opposite side. So that's why you always get the anti-addition or the trans product. All right, just to remind you about all that stuff. The trans product. Okay. And here's just another view, just kind of showing you how the bromine, this is kind of more of a three-dimensional view, how the bromine sits on top. Imagine this is a gigantic bromine. This bromine has to come from underneath in order to give you the trans product. And then the addition of H2, so hydrogenation. using a platinum catalyst. So platinum, the hydrogen goes cis in this case. You can also use a palladium catalyst or just platinum metal or platinum oxide. It doesn't really matter. Any one of those three is fine. I kind of just show you this quick little, I guess it's a mechanism, but it's not something that you need to know for the exam. Just kind of showing you why it goes cis is that our double bond kind of, floats down on top of this, and the hydrogens are right there to actually pluck on. The hydrogens absorb onto the actual metal itself, and that's why it has to go on the same side. So you always get cis products. And then 4.6 is the oxidation. So we talked a lot about this before we left, and we did a lot of problems. So you guys should be pretty comfortable with these oxidations. There are three types. There's epoxidation, hydroxylation, and then the oxidative cleavage one. Remember, in organic chemistry, if you gain oxygens, it's oxidation. If you lose, it's reduction. The epoxidation was MCPBA. You can form the epoxide. All right, so this MCPBA is what's called a peroxy acid. Basically, it's a carboxylic acid with an extra oxygen in it. And again, these are all the ways that the book shows you how to use this. And as far as I'm concerned, you can do either one. You can do RCO3H, R-carbonyl OOH, or MCPBA. Just make sure that you know that all three of them are epoxidizing agents. And then here is just a reaction that you can do with an epoxide. You can take the epoxide, add acid and water, and you form the transdiol. And the mechanism is where this protonates with acid to form this O+. And then the water, again, has to attack from the opposite side. So it's the same type of mechanism as with the halogens that we just saw. When the two bromines attacked, the big bromine was on one side, so the other bromine has to attack from the opposite side. This is the same type of analogy, where your oxygen is on one side, and the water has to attack from the exact opposite side of that. Pops it open, you have a proton transfer, like how we saw in the addition of acid and water. I'll do it in a second. All right, and you form the transdiol. All right, so here's just another example, just to kind of show you a real-life example. MCPBA to give you the epoxide, and then acid and water to open it up. Now, you don't always have to add acid and water to get a transdiol. If you just want the epoxide, then you just have the epoxide. After what we've learned in Chapter 7 with SN1, SN2, what you can do is you can add any type of a nucleophile. It doesn't have to be acid and water. You can add any type of a strong nucleophile. Do you guys remember what strong meant? All right, that meant having a negative charge on it. All right, so you can add any type of a strong nucleophile to this, and it's going to add onto this, and it pops open our epoxide. All right, so step one is usually adding any type of strong nucleophile. I gotta go backwards on this thing. Step two is adding acid afterwards. All right, so if you just add, so let me actually, let's actually do this. Let's do a practice problem. You guys should be able to see this. Yeah, you will. Okay, good. Okay, let me make this a little closer. All right, this would be my board. Okay, so let's take an epoxide. Let's take that cyclohexane epoxide. So there's oxygen right there. All right, the first reaction is I want you to add NH2 minus to it. And then the second step is to add acid. See if you can figure out what's going on there. Okay, remember that nitrogen with the 2 minus has 2 lone pairs of electrons. Okay, so see if you can figure out the product. What might help is to draw an actual mechanism. So first you're adding this. So show me, remember, here's our nucleophile. I know it's my nucleophile because it has a negative charge. All right, it's going to obviously attack the partial positive carbon. It's going to open up the ring, show me what that intermediate looks like, and then protonate it with acid. All right, I'll give you guys about 5 minutes, and then after this, I think we'll take a quick break. Okay. Okay. So what's basically going to happen is I'll draw out the mechanism for you so you can see what's happening. So remember, always think mechanistically. Think about your nucleophiles. Think about your electrophiles. So these are your lone pairs. Here's your epoxide. So these lone pairs are going to attack one of the carbons from the opposite side, opening up the epoxide. Okay, so an intermediate is going to be the cyclohexane. All right, your oxygen is now going to have a negative charge. And now, what's attached onto this carbon right here? It's going to be that nitrogen. So the nitrogen is now attacked. So basically, that diol reaction is where water is your nucleophile. So in the other case, we had water, we had oxygen attack. In this case, nitrogen. The point is it doesn't matter what your nucleophile is at this point. You guys can add any strong nucleophile, all right, and it will open up the epoxide. And then the second step in adding acid protonates this O-. So your second step is where you add acid, which basically puts a proton on that O- charge. So your final compound should be your alcohol coming up and your, what's an alcohol? and your amine group is going down, and H2. Sorry for that. Does that make sense? All right. Again, obviously I can't see who's shaking their head or whatever, but if you have a question, please type it in or unmute yourself and tell me that you don't understand or you want me to go over it again. All right, you know what?
Hello?
Yep. Yeah.
Can you just really quick go over the second step?
On
the acid.
On the acid, yes. So on step 2, I'm adding acid to it. So if you notice, I have a negative charge here. So, and acid is a positive charge. So basically, what I'm doing is I'm putting a proton back on that O- charge. I'm protonating it. So at the moment, if I add NH2, this oxygen right here, it becomes an O-. And then by adding acid, it puts a proton on that O-, and it makes it into an OH.
Okay.
Okay.
Thank you.
Okay. Yep.
Yep. Does it matter which bond the NH2 attacks?
Oh, no. No.
Oxide?
No. It
Just
can
as long as they're trans?
Yeah. So if you got this as your product instead, it's totally fine. So what you're probably saying is you probably got like the NH2 there.
Yes.
And you got the OH here. Yep. That's totally fine. Okay.
Cool. Thanks.
Yep. You're welcome. Good. All right. Any other questions? Because I'm gonna put one more on here just so that we can make sure that everyone has got it. Okay. I think the best way to clear it is just to close it and then reopen it. Figure that out. Okay. Let's do. I don't want to draw the cyclohexane again. So let's draw this epoxide. And this time, we're going to add an acetylide ion. You guys remember the acetylides? Which we'll talk about at the end of this chapter. It's supposed to be a lone pair there. Looks like a little ghost face. That's kind of ridiculous. And then 2, add acid. Okay, so if you guys show me the product of that reaction. If you want to, here, we can make this into a wedge right here. It doesn't really matter in this case just because I can't really do it without deleting the actual. That looks so horrible. Okay, so in this case, it's going to be your carbon is going to attack. And again, it can attack either one. It won't really matter in this case. But your carbon, so notice we're making a carbon-carbon bond. So that's going to attack that carbon right there, and these electrons are going to kick in there. And again, if you attack there, it's fine as well. It doesn't matter. So your intermediate, in this case, is going to look like you'll have the wedge for your oxygen here. So that will be an O-. And then you'll have your carbon acetylene attack there. Like that. And then the second step is adding the H plus in order to protonate it. So I'm just going to write the proton here, so I don't have to redraw this thing again. So that should be your final product. You should have an alcohol coming out towards you on one carbon, and then the triple bond going back on the other carbon. And again, if you have these switched, that's totally fine. Okay? This is just again, the whole point is just showing you that this reaction with epoxides, you basically add any type of nucleophile. So these are two different strong nucleophiles we learned about, NH2 minus, and then the acetylide one. Just put a negative there. But there are a lot more other nucleophiles. Pretty much anything that has a negative charge. This is really going to frustrate me. Okay, so it shouldn't matter what nucleophile you add. It will always do the same thing. All right.
And when would it matter which side the nucleophile is going to?
In this case, it doesn't, because we're not forming a carbocation. Anytime that we do a mechanism where you form a carbocation, that's when we have to worry about Markovnikov rules. In this case, if you just have a negative, it'll just add to either side.
Okay,
All
thank
right.
you.
Yep, you're welcome. It looks like all my programs closed down. But you know what? Why don't we take a break right here? Let's take like a 10-minute break. And when we come back, I think we'll probably be able to finish Chapter 4 and possibly even start Chapter 5. All right? All right. I'll see you in a bit. All right. Any questions on the last thing that we just did? I'm going to find the chat box. Okay. All right, dihydroxylation is the next reaction, where if you take a double bond plus KMnO4 and sodium hydroxide, you get the cis diol. You don't have to worry about a mechanism for that. I talk about this MnO2. I didn't talk about this in class, but that's basically what happens to the MnO4. These two oxygens get put onto the carbons, and so you get O2. And the potassium pairs up with a counterion with, I think, a portion of that OH. But again, it's not important what happens with all those. But that's why I wrote that right down there. So that's the dihydroxylation. Oxidative cleavage, talk about the three possibilities, depending on if it's a di-substituted, mono-substituted, or if you don't have any substitutions, if you just have two hydrogens. Here are the examples. Di-substituted, you get a ketone. Mono-substituted, you get a carboxylic acid. And then non-substituted, you get CO2. So here is just an example, just a generic example. Chemothermal acid and heat, cleaves it, puts an oxygen on either side to give you that diketone in this case. All right. If you have a hydrogen in one spot, you'll get a carboxylic acid. Here's just every possible example I believe I give you. All right, that should be a double bond right there. Let me just make sure you guys, I think you guys know, but just for completeness, that should be a double bond right there. All right. All right. All right. So, any questions on oxidations of carbons? Dihydroxylation, oxidative cleavage. Oh, I just stop sharing. Yes, I did. Sorry about that. Let's go to screen. Looks like it's not this. Okay. All right. Well, that's a very easy slide. 4.7 we're going to skip. 8, 9, and 10 is on resonance. So watch that on YouTube and in class, and we already did that. So let's go to that, and then let's get to the 4.11. All right, so 4.7 is on alkynes. So all the reactions that we've just learned with alkenes, we can do with alkynes, but we can do it twice. Here's just naming alkynes, pretty straightforward. You start closest to the side that has the triple bond, and then you name it accordingly, not where a substituent is. So since the triple bond is on the left side, that's where I'm going to start counting from. So this would be 6-chloro, hept, since it's 7, and then on the second carbon I start with a triple bond, so it's ended in -ine. If I have a double bond and a triple bond, we call them enines, and ene comes before -ine because ene alphabetically is first. However, whichever pi bond is, whichever one is closest to the end, that gets priority. All right. If you have a tie, then the alkene will get priority because of the fact that alphabetically it comes first. So the alkene has priority if it's tied, but if the triple bond is closer to a side, then that will get the priority. And here are the reactions. Excess hydrogen and platinum oxide, so it does not stop at the alkene. It goes completely to the single bond. So it just hydrogenates it. If you want to stop it at the double bond, we do Lindlar's catalyst. Adding 1 equivalent of HBr puts the bromine on the more substituted. 2 equivalents puts 2 bromines and gets rid of all the pi bonds. We talked all about this. X2, 1 equivalent, doesn't say it there, but let me just put it there just for completeness. The 1 equivalent of X2 just gives you the X's, but it keeps the double bond. With the 2 equivalents, you get all 4 of them become halogens. With the mercury and the sulfuric acid, you get this enol. We talked about this enol. You get a double. It's called an enol because you have a double bond, plus you have an OH. So it's called an enol, but it's not very stable. What happens is the H and the pi bond switch places. So the H goes to the carbon, and then the pi bond goes in between the carbon and the oxygen. And basically, it gives you the ketone. All right, so this is the product. So if I were to ask you, what's the product of this reaction, and the answer is that. All right, but I just want you to know that it goes through this intermediate. Okay. All right, and then it looks like I don't have a slide. I don't think I did a slide on the acetylide, did I? Because I think I talked about that in class. So the acetylide reaction, just to remind you again, but I think you guys know, but just to remind you. The acetylide reaction was you have a terminal triple bond. All right, it doesn't really matter what's attached here. Let's just put an R group. And the first step is you add NaNH2. And remember, that plucks off the hydrogen. So the nitrogen plucks off that hydrogen, and these lone pairs go on the carbon. So it gives you this. All right, can you guys hold on 1 second? All right, sorry about that. Okay, and you form the acetylide ion. And then remember that the second step is we always added that to some sort of alkyl halide. So remember, this has to be sp3 hybridized with some sort of halogen to it. Usually we use chlorine, but you can use bromine or iodine. And remember, these lone pairs attack the carbon and kick out the chlorine. All right. What mechanism did this go through? What was the name of the mechanism? See if you can remember. I'll give you a hint. This is a concerted mechanism. It's a concerted mechanism. All right. Hopefully you said SN2. This was an SN2 mechanism. So at this point, when we learned it, we didn't know about SN2 and SN1 and E1, E2, but then we talk about in Chapter 7 And I reminded you guys in lecture that this acetylide reaction is an SN2 mechanism. That's basically what it's going through. You have a strong nucleophile. I'll put SN for strong nucleophile. And you have an sp3 carbon. Obviously, you want this to be primary. We talked about that primary is more reactive than secondary, and tertiaries don't really go. Hopefully now, after learning Chapter 7 stuff and then going back to see this, that this reaction makes more sense. All right? So any questions? That's basically Chapter 4. That's all of Chapter 4. Any questions on Chapter 4? I'll just look through my notes real quick to make sure there's nothing in this. I also talked about resonance on that as well. So we did a bunch of resonance practice problems. All right. I don't see anybody saying anything. So, oh yeah, Morgan, are you? Were you able to log back in? You asked about the turning in assignments. I don't know if you caught that. I read these at the break. The turning in assignments is that you will post them on if you go to assignments.
Right, I just wasn't sure if you wanted us to actually take a picture with our phone and turn it in that way, or if you actually wanted us to scan them using.
Yeah, if you can scan them and create it into a PDF, that would be great, because
okay, cool.
Yeah, because a picture is kind of hard to read it, but
Totally.
if you get any of those programs, or if you actually have a scanner, yeah, I'd appreciate that.
Okay, perfect. Thanks.
Yep, and then is the sound better? I think the Morgan too. I think you asked me about the sound. It was going in and out.
It's been pretty good.
Okay. All right. Good. All right. Let's go back to assignments. Okay. Any other questions on Chapter 4? Do you guys feel pretty good with Chapter 4? Have you guys done all the synthesis problems? You remember these? I'll bring it up right here. Oh, Chapter 4 slides. Is that it? Okay. So it was all these. We have to start with the acetylide ion. I seriously have Chapter 4 right here. I think that was it right there. There's the Chapter 4 slides. But I don't think I have any other chapters, which is weird. Okay. Okay, so let's go to Chapter 5, which is aromatic. That's probably the last thing that we'll do. This is really not a lot in the chapter. Lecture notes. I'm sorry, not Chapter 5, Chapter 5. Yeah, here it is. Well, let me download the whole thing, so it'll be easier. Do it. Okay, whatever. Okay, so Chapter 5 is on aromatics. So everything that all the reactions that we just learned in Chapter 4 do not work on aromatic rings. Just because I have pi bonds doesn't mean that those reactions work. So here I'm showing you if you try to do hydroxide, or if you try to hydrogenate it, you don't get any reaction, because the aromatic part of this ring is what makes the ring special. It makes it very, very stable, and it doesn't want to break up the aromatic part of this. So we have a whole bunch of special reactions in Chapter 5, and the reason is because of resonance, because of the fact that we have this resonance. It takes much more energy in order to break those pi bonds, so the activation energy is incredibly high, so it won't do it. 5.2 is on naming. So naming is pretty simple. If you have a simple molecule, you just name the substituent that's hanging around it. That's good. I can highlight that. And then you end it with the word benzene. So bromobenzene, ethyl benzene, there are these common ones that I want you to memorize. So if you have a carboxylic acid, it's called benzoic acid. Methylbenzene is called toluene. All right, and if you have an OH, it's called phenol. All right. Okay. So that is naming. I think there's a little bit more naming, isn't there? Yeah. Okay. So if you have an NH2, it's called aniline. That doesn't look too much like an N, but that is an N. Trying to get this pencil. It takes a while for it to load. So that's an NH2. That's called aniline. All right. So the reason you have these common names like benzoic acid and toluene and phenol, notice it ends in -ol because it's an alcohol, or aniline, is because if you have a compound that has like 2 or more groups on it, and one of the groups is one of those common names, that's what you're going to name it as the parent. All right, so that's carbon 1, and then you name all of these substituents hanging off of it with respect of that methyl group at carbon 1. So at the 2, the 4, and the 6, I have a nitro group. So this is called 2,4,6 trinitro-toluene, which is also is TNT. All right. Oh, cool. So you made flashcards. So if you guys want to use that link for more flashcards, I like those. I'm glad that you guys are doing those. All right. Other naming is if you have a 1,2 substituted benzene ring, it's also called ortho. And if you have 1,3, it's meta. If you have 1,4, it's para. So the name of this compound would be ortho-bromochlorobenzene, because alphabetically, bromine comes before chlorine. Or you can say 1-bromo-2-chlorobenzene, or rather than saying the word ortho, you can just put O. So any of these 3 are fine. Parachlorotoluene. So notice here's one of those common. Here's one of the common groups called toluene. So, and then you have a chlorine that's para to the methyl. So parachlorotoluene. Instead of saying parachloromethylbenzene, you can just call it a toluene. All right, here's, you don't have common ones, but you have 3 substituents. Label it by whichever one comes alphabetically first, and that the numbering is the lowest. So you're looking at ethyl versus chloro. Chloro comes before ethyl, so that's going to be carbon 1. Bromine's carbon 2, carbon 3. Now, bromine technically alphabetically is all before everything, but then you would have to label it like 1, 2, 3, 4, 5, 6. 1, 2, 6. And we learned when you name alkenes, you always want to have the lowest values in your numbering. So rather than doing a 1, 2, 6, you start, it's a 1, 2, 3, and you start whichever one of those 2 alphabetically is first. But when you name it, you still name it alphabetically. So 2 bromo, 1 chloro, 3 ethyl benzene. Now, what happens if the group hanging off your aromatic ring is very complicated? So if you look at this group, again, let me get the annotate pencil. Come on. So if you look at this group right here, this group is pretty complicated, right? It's not like a straight, excuse me. It's not a straightforward ethyl or methyl or something. So if that's the case, this becomes a substituent, and it's called a phenyl ring. All right. So when that's the case, you name it like you would name an alkane. Look for your longest continuous chain of carbons, and you name it alphabetically. So this is 3-chloro, because if you look, here's my chain. Here's carbon 1, carbon 2, carbon 3, carbon 4, carbon 5. The third carbon has a chlorine. The second one has a phenyl ring, and since it's 5 carbons, it's a pentane. So in this case, phenyl is used as a substituent. Okay, so there's 2 ways of naming. One is where the aromatic is the parent, and the other is where the aromatic is a substituent. go to the reactions now. So 5.3 is the reactions. All right, so basically these reactions are what's called electrophilic aromatic substitution, where you're adding an electrophile to your aromatic ring. And basically what we're doing is changing the electrophiles. Okay, this is a chapter 4 reaction, adding Br2 to a double bond. In this case, because we're adding it to an aromatic ring, it doesn't do anything. So you have to add a catalyst. And in this case, our catalyst is iron bromide, or if you're adding the chlorine, it's iron chloride. Whatever halogen that you use here, that's the halogen that you have to use in your catalyst. Okay? So Br2 plus iron bromide puts a bromine on there. Br2 plus Cl2 puts a chlorine on there. That's a quick slide. .4 is adding nitric acid, and you nitrate it to form a nitro group. So in this case, you have to add an acid catalyst. So remember, anytime you do acid catalyst, you can actually write the catalyst or write H plus or H3O plus. Okay, SO3 to make a sulfonic acid. This is called sulfonic acid. And then 5.5 is Friedel-Crafts alkylation, and there's also the acylation, which is probably on the next slide. But the alkylation is where you have to have an sp3 carbon plus a halogen. Usually it's a chlorine, and you add AlCl3, and you can attach the actual carbon group directly onto the aromatic ring. All right, so here's an actual example of that. So that's the alkylation, and this is probably the acylation. Here we go. Here is the acylation. So acid chloride plus AlCl3, pops it on there, and it gives you the ketone in that case. Okay, so any questions on the reactions? You guys good? Okay. The substitution effect. This is the orthopara or a meta directing group. So if you have a mono substituted aromatic ring and you want to put on a second group onto it, remember this group that's already on the ring has an effect on where that group is going to go. It's either going to go in the ortho and the para spot as an orthopara directing group, or it's going to go in the meta spot. All right, and we talked about how you can tell the difference between if the group is going to be orthopara or meta. If it's orthopara, remember if it has a lone pair, it's going to be orthopara. Or if it's sp3 hybridized. Okay, so groups are either orthopara or they're meta. So orthopara, here's an example of orthopara because oxygen has a lone pair. You basically get a mixture, a higher mixture of the orthopara, mostly the para, because this group, your OH group, kind of blocks these groups here, so you get more of the para. But you can see you barely get any meta. All right, here's an example. So cyanide, remember, is a triple bond. Let me draw the C. Oh, I got the marker. It's a C with a triple bond N. So we talked about if you have a pi bond directly attached. So if there's a pi bond directly attached to the aromatic ring, that's a meta directing group. So if you look down here, if it's an sp3 carbon, it's orthopara. All right, see orthopara. If you have a lone pair, it's also orthopara. Here's examples: OH. If you have a nitrogen that has a lone pair, or a halogen. All right. But if you have a pi bond that's directly next door to the aromatic ring, like cyanide or carboxylic acid or ester, or a ketone or an aldehyde or an amide, any of those nitro groups or a sulfonic acid, those are all meta directed groups. All right, so in short, lone pairs are sp3 is orthopara, and there's a pi bond, it's meta. All right, so here's just a quick reaction. This is sp3 hybridized. So if you add AlCl3 to it, you can get the orthopara. you have a carbonyl, or in this case a pi bond, and add Cl2, you'll get just the meta product. But pretty much we're going to assume that the para is our major product. All right, the last reaction is the oxidative cleavage of the benzylic carbon. Remember, the benzylic carbon is the carbon directly adjacent to the aromatic ring. You have to have at least one hydrogen on there. And then you can oxidize it. Basically cleaves everything off and it turns it into a carboxylic acid. Sorry, find what it is. There it is. Okay. So it has to be sp3 hybridized, and you have to have at least one hydrogen. All right. So here's sorry about that. Here's an example. You can have 2 R groups, 1 R group, no R groups, but you have to have at least one hydrogen plus KMnO4 and water, and you basically turn it to a benzoic acid. All right. So here's an ethyl group, benzoic acid. This obviously is a very exaggerated. It doesn't really matter what there is. This whole entire thing gets completely cleaved off, and this aromatic ring becomes a benzoic acid. Obviously, this other stuff it turns into stuff, but we're not concerned about that in this reaction. All right. So here's kind of I like this reaction. It kind of shows everything. Here's a methyl. Here's an ethyl. Here's a tert-butyl. Notice I have an sp3 carbon right here, but notice there is no hydrogen attached to it. Okay. So because of that, if you add the KMnO4, it will oxidize these 2 carbons. All right. It oxidizes those 2 carbons, but it won't oxidize that carbon. So you get these 2 carboxylic acids, but nothing happens on that one. All right. And then what's this section? I'm going to skip 5.9. And then 5.10 is just basically more on synthesis. Okay. Okay, so that's all I kind of want to talk about today. Unless anyone has any other questions or wants to talk about anything else, we can do that. Otherwise, tomorrow we're going to go over Chapter 7, and then we'll actually do some problems as well, exactly how we did like today. So this will basically be our review for the exam next Tuesday. And like I said, I'll post the quizzes for those chapters, 5 and 7. You'll have till next Tuesday to take it. And that's pretty much it. Does anybody have any other questions or anything they want to talk about? Feel free to email me. Make sure you're checking on D2L. Otherwise, I will see you guys tomorrow. Yep, no problem. 19707, even though I know who you are. Yep, Anna, no problem. Is there a schedule for when we're doing labs? So I already talked about that. So like I said, I'm going to post a video that you guys will do, but pretty much there is no more labs. We aren't doing any more labs. But there's that one video that I want you guys to watch, and again, I'll post it on D2L and tell you all about it. Okay, good. Oh, thanks. Yep, no problem. Yep. And then, again, if there's any labs that you guys haven't handed in yet, and if you have them, post them on the online, and I'll grade them accordingly. All right? All right, guys, I'm going to end the video. See you guys tomorrow.